There's an issue with Canvas, I believe, when it comes to seeing grades. There's a message that was posted by CITS on the 24th, mentioning there was some issues there. I've made some changes to the grade book, but I'm assuming that you guys cannot see it. So I'm gonna ask you guys to, if you want, before I can talk to CITS, I have not been able to talk to them today, but I will after class today to make sure that all of my information can be viewed from you guys. So if you want to pick up your exam, I would say tomorrow will be the best day, all right? Take a look at your Canvas later today to get that update on your exam one scores. There's just an issue right now going on with that. There's probably several messages that you guys did not receive from me, all right? So the first thing I want to say is that exam 2 is scheduled for October the 9th. I believe that's Friday, all right? So that should be coming up during your midterm week. It's the last day in the midterm week. That Friday, you will have exam 2, and that will cover chapters 3 and 5, all right? I'm gonna try my best to get a study guide typed up with all the different topics and the practice exams posted soon, all right? Soon can be up to Wednesday or this Friday, but keep in mind that October the 9th, if you want to, please schedule that in your schedules and your calendars that you will have an exam on that day. Again, we'll do the scheduling for that, for those that want to come in person. And for anyone that needs to do it online, just send me an email so that I can kind of get the names that, or you can use that same scheduling sheet to identify yourself as wanting to take it online so that I can work through that. There's still one student that I'm working with online. Hopefully we can schedule a time today to talk about exam 1. I think there's some issues there. That's okay. Don't feel bad. That's just how things are going. CTIS is having issues with Canvas. There's just a lot going on. I think that's happening. What's happening is that we're having to rely a lot on the virtual online tools, and they're probably being, used and pushed at a limit that they haven't been used before. So it's just taking some time to get everything clear. So it's going to be rough, probably up until midterms, but hopefully after midterms, every potential issue we've already run across that we'll be able to circumvent those problems soon. All right. So hopefully CITS will have Canvas back up and running, and you should see a trail of messages that I tried to send you guys this weekend. I'm also updating the extra credit that you guys had from Dr. Holder, Dr. Tanner, as well as the University of California, Irvine, and we're talking to you guys last week. So again, I'll probably send a message, and hopefully I'll check with you guys on Wednesday that you receive your messages in your exam 1 scores, all right? If you want to pick up your exam 1, again, you can schedule a time to just come by my office tomorrow, all right? I got office hours from 9 until 11 o'clock, and then from 1 to 4 on Tuesdays, all right? So I have 2 individual times for office hours that you guys are more than welcome to stop by my office, okay? All right. With that said, actually, let me do this. Let me do a review because it's been a while since we talked about chapter 3 material. All right. And I know that we went through confirmations quickly. So I want to make sure that we are comfortable with this again. So let's start here. Okay, so right now we're in chapter 3. The first half of chapter 3 has dealt with nomenclature, and there's a quiz that you probably can't see. I don't think I didn't even make it available because I was getting so many messages from my other classes this weekend. But there's a chapter 3, there's a nomenclature quiz in Canvas. I'm gonna try to call them directly and they'll work with me to see if they can see it on their side. If they can see it, then we're gonna assume that most likely students can. So I'll send a message, and I'll also put a notice to let me know that you can see it so that I can confirm that that the class is receiving that message. But there's a quiz on nomenclature that will be coming. If I can't do it today, or we'll do it Wednesday, or we'll do it Friday. It doesn't matter. We just want to get that quiz in before the exam. All right, so we will, the first half of chapter 3 dealt solely with nomenclature. All right, you guys know how to name organic molecules. Hopefully you've been practicing with the dynamic study modules and the questions that are built into the chapter 3 homework. All right. Again, there are maybe 4 main rules that you guys want to have mentally when it comes to naming. All right. I can't express this enough. Those rules have to become a part of you, right? First, you need to identify the parent chain. All right. You want to be practicing identifying the parent chain. All right. Keep in mind the parent chain has to be the longest alkyl chain. However, sometimes there are ties where you count the number of chains and there's 2 chains that have the same length. In that case, you want to choose the chain that has the most substituents. All right. The longest alkyl chain with the most substituents is the parent chain. All right. So make sure you guys are practicing identifying that. The second rule says I need to number the chain correctly. And keep in mind, there's always 2 ways to number a chain. You want to choose the numbering that gives your substituents the lowest possible numbering. All right. There are potential ties that can occur, right? And when you have a tie where your numbering gives the same scenarios, or which are the substituents are the lowest, then you want to give the priority or the lowest numbering to the carbon that has the highest priority. All right. So keep that in mind. To break a tie between numbering substituents, give the lower numbering to the carbon that has the highest priority. And how did I determine if a carbon has higher priority? By the atoms attached. All right. Higher priority atoms have higher atomic numbers. We cover that, some examples of that in the lectures that we have in the past. All right. Rule 3 says deal with substituents. All right. And substituents have a lot of different flavors. All right. First thing with substituents, I need to indicate is location. Is it located on carbon 2 of the parent chain or carbon 4 or carbon 5? All right. So make sure you know the location of your substituent. Have you named the alkyl group correctly? All right. Have you considered branching? Is it a Sept butyl group or a regular butyl group, or is it an alpha group? All right. Or is it a tert butyl group? So you want to make sure that you've named the substituent correctly and you have it in its correct position. The last thing with substituents is to consider any multiplicity. All right. And that's multiples of the same. If you have 2 methyl groups or 3 alpha groups or 5 cyclopentyl groups, you want to make sure that you express that multiplicity correctly when you're naming substituents. And the last thing is to name your compound now. Start with alphabetical order of your substituents, then give the parent prefix in with the parent name functional group. All right. I'm going to leave that to you guys. You guys are going to be responsible and use all tools possible to practice naming. All right. There was a practice worksheet that I posted in Canvas for you guys to practice naming molecules. And I've only had 2 students to come by to even go look over those. All right. So I'm assuming that you guys are comfortable with naming. All right. I hate for anyone to say, oh, me and my other colleagues can't name. That's typically how students like to approach me, right? They like to say not only can they not do it, but all their friends in the class, they can't do it either, right? You guys want to gang up on me and say, oh, Dr. Cooper didn't cover that. All right. I'm not going to feel guilty this time around, right? I gave you guys homework assignments. I posted practice examples as well. We covered nomenclature, all right? So make sure you guys are comfortable with that. All right, the second half of chapter 3 is what we're dealing with today, which is in conformations. We talked last class that said that organic molecules that are just involved in single bonds, conformers are just involving rotations around bonds, right? And so we talked about last class that there's being like 3 main ways of showcasing that type of, or showcasing conformers around single bonds. You can have a line wedge perspective drawing. All right. You can have a sawhorse drawing. And then lastly, you can have a Newman projection. All right. We mentioned that the Newman projection is the workhorse. All right. That's typically how people like to draw acyclic conformations. These are conformations of molecules not in rings. They will draw it in a Newman projection. All right. From this slide, we get some very important information. This cross point here between these 3 lines indicates the front carbon, and this big circle here indicates the back carbon, right? I was able to showcase or show you guys from the molecular visualization program how you can use the model kits to try to represent a Newman projection. That's just looking straight down a chemical bond. All right. We also learned that there's 2 major conformations, And we learned that there's one that's preferred and the other that is not preferred, all right? We learned that there's a staggered conformation versus an eclipse conformation, all right? This is staggered, this is eclipse. What's important in staggered conformation is that there's 60 degrees dihedral angle between these two hydrogens. I'm sorry. In the eclipse conformation, there's a 0 dihedral angle between the two conformations. Can anybody tell me which conformer is preferred, the eclipse or the staggered conformation?
Staggered.
The staggered is preferred. How do we know that?
It's lower in energy.
There you go. Bingo. Is lower in energy. If I look right above here, I realize that this staggered conformation has the lowest possible energy. However, the eclipse is unpreferred or not preferred because of what? It's higher in energy, right? You guys have these slides. Be comfortable with that, right? I know that anything that's higher in energy is always going to be unstable. That's what instability means, is that I'm just higher in energy. I have not relaxed myself. Instead, I'm energetic, right? And molecules that are typically energetic are higher in energy. So what does this really mean? If that's curious, if there's a question that comes to your mind that's curious, this molecule is high energy, what happens here? Whenever this molecule adopts a eclipse conformation, it puckers or it rotates right out to the stagger. That's exactly what it means, all right? This molecule will not persist like this. There's enough energy to promote a rotation to where all bonds are what? Staggered, all right? Keep that in mind. Okay, I'm gonna move through this and we start to learn that there was some new things that can come up if I consider other atoms attached around my Newman conformation, all right, and my Newman projection, all right? There's some additional terms that come out. The first new term is something called a total eclipse. And what's unique about the total eclipse conformation?
It has two of the largest atoms eclipse.
Good. So if I had to look at the larger group on my front carbon in my Newman projection, what would it be for this molecule? The methyl group, right? And if I look on the back carbon, I had to identify the larger group. What would you tell me again?
The methyl group.
Methyl group, all right? So if the largest group from the front and the largest group from the back have a 0 angle, they're staggered, we call this a total eclipse. And this is the worst conformer you can have, all right? This is the worst conformation possible. That means that this molecule will rotate away as soon as you do it. As soon as the bonds are in this position, they rotate out, right? It becomes so unstable, it has to rotate, right? All right, we also learned that in staggered conformations, if my two largest groups, the one from the front and the one from the back, are 60 degrees from each other, we call that what type of interaction? A gauche interaction, right? And this gauche interaction is worse than a typical stagger, right? So I would love to have these two large groups furthest away from each other, right? Instead of having them close to each other, okay? Now we have another eclipse conformation here. However, is not total eclipse because my larger atom on the front, which is a methyl group, and the largest atom in the back, which is this methyl group, are not directly in front and behind each other. Instead, they're 120 degrees apart. So this is just eclipse, but it's not total eclipse. All right, I have another staggered conformation here, but my largest atom in the front is a methyl group that's down here, and my largest atom in the back is another methyl group that's up here. They have 180 degrees from each other. What do we call this type of staggering? This is an anti-stagger, and this is the preferred conformation. All right, this is the most stable conformation for acyclic compounds. All right, so we want to get rid of these interactions. And what do we call these interactions between these large groups? What's the term that we like to say in organic chemistry? S. sterics. That's right. There's steric interactions, right? So whenever I leave sterics, but having these two groups 180 degrees from each other, we call this a preferred conformation, right? Or an anti-stagger. So if I look energetically here, right, I realize that the anti-stagger is the lowest, right? And then I see that my gauche stagger are next to energy, right? They're not the lowest, not too far off. Then I go to my eclipse confirmations at the beginnings here. Those two confirmations are the highest energy. And then I have in the middle here, two more eclipses that are not total eclipse that are second highest in energy, right? So this pink line is saying the highest that's coming from all my total eclipse. The green lines are saying now my next eclipsing interactions, all right? The blue line is coming from my gauche staggered, and the line that's black at the bottom is coming from my lowest energy, which is the anti-stagger. All right, so I'm thinking now that the class is getting pretty comfortable with that. All right, again, this is what happens when this molecule adopts this zero dihedral angle. So this carbon and that carbon are directly in front and behind of each other. So this is an eclipse, this is a total eclipse, and this total eclipse conformation has steric strain. All right, this molecule will not prefer this conformation. Instead, it will rotate itself out. So we need to alleviate this stress. Okay. Let's see. This is this. We're gonna get to these rings here shortly. So let's go and do another example of conformations. All right. Can you guys help me do this really quickly? Can you guys give me the highest and lowest energy conformer of 2,2-dimethylbutane? All right, and I got two examples that I want to focus on. We want to make sure we got this down. I want to look down carbons 3 and 2 in one structure, and then I want to look down carbons 4 and 3 in another structure. All right, can you guys move around a molecule to correctly give the Newman projections? All right. Any questions here so far? All right, no questions. First thing I would do, first of all, is draw a line angle structure of 2,2-dimethylbutane. Can you guys help me out with that? How many carbons in that structure?
4.
4 carbons, and what should happen on carbon 2?
You have 2 groups attached to it.
All right, is that correct?
No.
All right, somebody told me no. Help me out. Let me get a pen. Can I get a pen for this?
It should be one up, one down, not on the same side because it look like turk.
Okay. I can't get a pen to show up. Oh boy. Okay, we got it. All right, I'm gonna number these carbons. All right, 1, 2, 3, 4. Is this wrong or right?
I thought
right,
you
someone-
said the drawing was wrong.
No, I didn't. I asked you guys was it wrong or right. Somebody told me it was wrong.
It looks like turk.
Okay, there's a turret. It could look like a turret butyl somewhere. All right, this molecule is correct, right? I didn't start my 1 on the left-hand side. Instead, I started my 1 on the right-hand side, but this is right, right? If I had to number the chain, right, I had to put 1 here, 2 here, 3 and 4, right? Why did I have to number this way? I had to number to give my substituents the lowest possible number, right? So this is 2,2-dimethylbutane. Keep in mind, these molecules can be flipped, drawn different ways, right? But ultimately, we all have to share the same way of numbering, and that will give the correct name. Okay, good. So I drew my molecule out, right? And I'm interested in looking down only this bond right here. Can I make it red? Oh boy, it looks crazy. All right. So I'm hoping everybody's comfortable with that so far, right? But which carbon is in the front and which carbon should be in the back?
The 3 should be in the front and the 2 should be in the back.
That's correct. That's correct. So the carbon I give first should be in the front. So you guys want to keep that in mind. Oh boy, this is not going to look helpful. All right, I'm going to erase that. All right, hopefully you guys are hearing me and can remember that. All right, the carbon that's in the front will have to be the carbon that's given first will have to be the front carbon. All right, and the carbon that's given in the back will have to be the back carbon, or the carbon that's given second would be the back carbon. All right, so what do I see on carbon 3? Can you guys help me out? Just on carbon.
One
And
carbon.
two
A methyl group and 2 hydrogens. And what's on carbon 2? What do you guys see?
You have 2 methyl groups and a hydrogen. Oh, what? 3 methyl groups?
Yep, just 3 methyl groups, right? So if I look at my lowest energy conformer, right? This would be 3 in the front. I can't draw. All right, it's not gonna let me draw. Sorry. I'm just gonna have to use a laser pointer. All right, but if I look at my lowest energy conformer here, this is my carbon 3 in front. This has 1 methyl group, 2 hydrogens, right? Don't forget, 3 has 2 hydrogens that's understood. And on the back carbon, which is the big circle, I have 3 methyl groups. So this will be my lowest energy conformer, right? You might say, well, Dr. Cooper, there's some Gaussian interaction with this methyl group here, right? But this methyl is going to see always a methyl in the back. So there's no way to rotate this carbon away from those methyls. So this is the lowest energy you can get. My highest energy conformer will have my methyl group, which is the largest on carbon 3, and another methyl group, which is the largest on carbon 2, what, to each other? Eclipse, right? Right, so that gives me my highest energy conformer for that molecule. Any questions from the class? Okay, can we do the same exercise from the same molecule, but instead looking down carbons what now?
3 and 4.
All right. All right, so this time I need carbons 4 and 3. So which carbon's in the front this time?
4,
And which carbon's in the back?
3.
3, all right? So can you help me? What's on carbon 4?
You gotta. Would you have 3 hydrogens?
Yep, carbon 4 has 3 hydrogens, and then obviously there's carbon 3 in the back, all right? And what does carbon 3 have?
2 methyls.
2. Oh, be careful with carbon 3. I don't see any methyls attached to carbon 3.
So you have 3 hydrogens too?
No, carbon 3 has 2 hydrogens and all of this, right? Which would be a what?
You said all of what? Oh, so that's
All of
a.
this. All right, I'm going to erase it. This is a total of 4 carbons. You guys know this constituent name. It's called a
Terp.
it's a tert-butyl group, right? So now I look at carbon 3 here. Do you guys get this bar down here on your screen? Let me check. I can look and see. Oh, yeah, you guys get that crazy bar. Why am I getting this bar today? One second. All right, I can't get rid of that bar. All right, somebody got their mic on. That's all I hear in the background is a whole bunch of noise. Yep. Give me one second. I'm just trying to slide this stuff up. So.
Huh?
ahead one more time.
And my question is like, how do you know how to orient how do you know how to orient a group?
Can you speak up a little bit? I can't hear you too well.
How do you know how to orient a group on the or on the
How, how do I know how
circle?
to say it one more time?
So how there's like methyl for the lowest energy staggered on the C3 to C2. How do you know where to put what?
How do I know where to put what?
Like how do you know that methyl group goes right there? How do you know that hydrogen?
Yeah. Okay. Let's look at the molecule as it's drawn, right? So you want to go back to carbon 3 and 2. So if I look at carbon 3, right, which is my front, right? Carbon 3 only has a methyl group that we label 4, right? And 2 hydrogens attached, right? All right. And since I know that I'm going to deal with carbon 2 later, I just ignore it for now. All right. So I'm looking at what else is there. 2 hydrogens and 4, right? Then I go back to deal with 3, because sure, 3 is attached to 2, but 2 is drawn as that big circle. What's attached on 2, right? If I look at 2, sure is attached to 3, and I know that already. I don't have to worry about that. But there's 1, 2, 3 methyls on 2. So on the big circle on the back, I got to have 3 methyl groups that are there. If I look at this from carbon 4 to 3, carbon 4 has 3 hydrogens, right? And sure, it's also bonded to 3, but I'll come back to that. So let's deal with the 3 hydrogens on 4. So 4 is this carbon in the front that has 1, 2, 3 hydrogens, as drawn here. And don't forget that those hydrogens are understood, right, to be drawn for my language structures. And then if I look at 3, I have to deal with everything else that's not 4. So 3 has 2 hydrogens in this 4 carbon group here, right? So again, carbon 3 is in the back. So carbon 3 is that big circle. I got 2 hydrogens in this 4 carbon thing that is branched as a tert butyl group, right? So TBU stands for tert butyl. Okay. This is my lowest energy conformer, and my highest energy conformer has everything eclipsed. All right, there was another question coming through. Go ahead. Was there a question?
I got another question. So the
Okay.
circle is the back or the front?
The circle is the back, and the line in front is the front. Let me go back one more time. All right, so one more time. This carbon right here is the front carbon, and the big circle is the back carbon. All right. Good, 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 good. All right, let's keep moving forward. All right, so there's going to be some questions on confirmations. There's going to be some potential questions already built into your Pearson assignments. So if you have any additional questions, please come see me. But you want to make sure that you can take any structure and investigate it in its Newman projection, right? And that comes through practice, right? So you want to practice saying, hey, I got a new molecule. Can I draw it in a Newman projection looking down carbons 2 and 4? You can make any question that you want, and then you can investigate it. Is this the highest or the lowest energy conformer? All right. You also want to prepare yourself to look at different conformers and tell which one is the highest energy and which one is the lowest energy. All right. And if I got some time, I'll try to go back and see if I can bring up some questions where we can look at that. But I'm running out of time, and I want to move forward into the next portion of chapter 3 because we definitely need to start chapter 5 next class. All right. So we've been dealing so far with acyclic. And what does the word acyclic means? Can anybody help me out? What does that mean?
There's no ring.
No ring. All right. So now we need to look at cyclic conformers, right? This is a little bit more difficult, but we're going to start working here. What happens if I have a ring? All right. And you guys realize that the rotation is weird now, right? I cannot easily rotate out of a ring, right? These atoms are somewhat locked into its positions. All right. So that means that they're going to adopt unique conformations. And we want to get comfortable with cycloalkanes, right? Okay, I'm not gonna, there's some mistakes, well, not mistakes, but there's some things that we already covered. So there's a word that comes up, and we're going to define this as ring strain, all right? And you guys want to write this down, what I'm saying, all right? Because the PowerPoint slides, they talk about it, but they didn't combine it into ring strain, all right? Ring strain is a combination of angle strain and torsional strain. All right, we're going to try to break down those two terms as well. All right, so to understand conformation of cycloalkanes, and again, these are alkanes in rings, we need to consider a phenomenon called ring strain. And ring strain is a combination of angle and torsional strain. So what is angle strain? I think this makes sense to you guys. Angle strains are deviation from the ideal bond angles, all right, for your hybridization. And you guys do know that a carbon that's hybridized to be sp3 should have what bond angles, or what ideal bond angles? If you're tetrahedron, what should be your bond angles?
109.
Yeah, 109.5 is the ideal bond angles for atoms in a tetrahedron. If I deviate from 109.5, right? If I'm compressed or if I'm larger than that bond angle, we call that angle strain. All right, molecules start to become very, very strained because of the angles that atoms have to adopt. All right, and the last type of strain that we need to talk about is torsional strain. All right, and torsional strain comes from the rotation of bonds. Right, you torsion, you think a torque from an axle in a car. Right, if you got a pickup truck, anything like that, you just want to have rotational power. Torsional strain comes in when you cannot alleviate eclipse conformations. So let's say that you lock into a ring and you have very bad eclipsing, and you want to rotate that out, right? But if you can't, when you cannot rotate, that bond builds up strain. We call that torsional strain. So a lot of times they're eclipsing atoms and they want to rotate away, and those atoms cannot. And all that energy gets applied to that bond. So that bond becomes very stressed out because it would naturally rotate out, but it cannot. So we call that torsional strain as well. Okay. And that torsional strain sometimes can weaken bonds, right? And you can weaken bonds so much that they can explode, right? That's somehow, these are how organic molecules can be used as explosives. Their molecules are extremely strained. They're awkward situations to where they release energy when they break bonds, and that is enough energy for an explosion. All right. So let's talk about our three main, there are going to be three major rings, and there's going to be, well, I should say we'll cover up to the 6-member ring. All right. So we're going to start with 3, 4, 5, and 6. Okay. So let's go with our 3-member ring first. All right. 3-member rings are the most strained rings we can have. All right. This is the cyclopropyl ring. All right. This is extremely strained. If you take a look at this molecule, you realize that this H is directly in front of that H. This H is also directly in front of that H, right? So these hydrogens are all eclipsed. Is that preferred? No way. All right. So already this molecule is strained because there's torsional strain that's present because of the fact that you cannot rotate the bonds. There's a question someone has? Was there a question? Okay. So this high torsional strain for this molecule. Also, if we look at the bond angles, all right, this bond angle is 60 degrees. When it wants to be what again? 109.5. So we compress the bond angles about 49 or about 50 degrees, right? So that deviation is also a angle strain. Go ahead. Was there a question? So cyclopropyl rings are extremely unstable. Why? Why would 3-member rings not be preferred? Can anyone tell me? Hello? Say that one more time.
is it because of what you just said, because of the 60 and 49.5, it's trying to be the 109.5?
Oh, somewhat, yeah. But I'll take that. There's somebody saying that I see this by bad angles, right? All you guys would just want to know for this class right now that the 3-member ring would not be favored because of high ring strain. And what is high ring strain? There's extreme deviated bond angles, right? And there's torsional strain because there are eclipsing atoms and bonds, right? So if you guys can program you guys to think about a 3-member ring as being strained, you're gonna learn a lot. And I know this is different because typically I'll have my model kits and I can prove that to you in class, but I can't do that right now. I didn't want to put I don't have any convenient way of putting myself on the camera, and I'm trying to use the tools that are available to me right now to teach, all right? So you just have to take my word for it, but you can see this, that a 3-member ring would not be favorable or favored because of so much ring strain, eclipsing atoms as well as these deviated bond angles. All right, let's go back to the 4-member ring, all right? If you guys look at the 4-member ring, the bond angles are 90. Is that preferred? No, right? 109.5, all right? So the bond is compressed at about 19.5 degrees, right? Now, the bonds are more compressed in the 3-member ring than a 4-member ring, right? But it's still compressed. And if I look at the molecule here, right? This H is directly in front of that H. So I have these weird eclipsing atoms, right? These hydrogens are eclipsing. So the bonds are building up torsional strain because they can't rotate to alleviate that. All right. So the 4-member ring is also strained, but it adopts let me go back. Okay. It adopts this puckering. All right. They call this a envelope, but this is not really an envelope for this one. All right. Where it tries to pucker out to give itself a preferred conformation. So the 4-member ring conformation is this envelope of pucker, all right, conformation that alleviates some of the torsional strain that's built up because of eclipsing hydrogens, all right? I hope that helps a little bit. So the 4-member ring will pucker out. The 3-member ring can't do anything. So its preferred conformation is what it is and is not stable. The 4-member ring can pucker a little bit to give a preferred conformation. All right. The 5-member ring adopts a envelope conformation. All right. And from the envelope conformation, there's going to be one atom above or one carbon that's kind of pucker up over the others. I actually do not like the way this is drawn here on the slides. All right. But if you look at some of the neighboring bonds, you realize that these hydrogens are not eclipsing. All right. And the bond angles become pretty preferred here. They're pretty close to 109.5 in a 5-member ring. I don't think I have the time to show a better representation of the envelope. Yes, ma'am.
So the more carbon rings you have, the more preferred you are?
No, not necessarily. You just want, it's what the ring can do. But that is a consequence of adding more carbons, yes, if you want to think about that. Going to a larger ring is going to somewhat be preferred, but you can go too large when the conformations become unpreferred again. So there's like an ideal position you want to be, all right? And the ideal position is the 6-member ring, all right? When you have 6 atoms in a ring, you're going to get a chair conformation, and this is the preferred conformer, all right? This chair conformation allows all your atoms to be staggered, and it gives you bond angles that are 109.5, okay? So the chair conformation is the most stable conformer of cyclohexane. There's no eclipsing interactions, and the bond angles are 109.5, all right? What's key to know is that the chair is not the only conformation for a 6-member ring. Instead, the chair is the what? The lowest energy conformer for a 6-member ring. So let's review really quickly what other possible conformations are present for the 6-member ring. All right. We have to spend a lot of time, or we study the six-member ring a lot because it's prevalent in organic chemistry. 5 and 6-member rings make up all of the biological relevant molecules that you guys know. DNA, sugars like glucose, or even make up starches and cotton and things of that, cellulose. All these materials usually contain 6-member rings, or if in some cases, some 5-member rings. All right. So let's look at the potential conformations of a 6-member ring. We got the 2 chairs. All right. That's very important to keep in mind that there's 2 potential chairs that a 6-member ring can adopt. Where if you look at this really closely, this chair on the bottom left hand looks like it's leaning towards the left. Can you guys see that it's leaning that way? And the chair on the right hand side is leaning towards the right. All right. Typically, when I can draw these on the board, I try to have a better, where you can see that a little bit easier. And I can use my computer software to show that in the next lecture, because I'm almost out of time, where we can start to see the differences between these 2 chairs. All right. A 6-member ring can adopt a half chair, a boat, a twist conformation. All right. And if we look at these, the chairs are the most preferred. The half chair are the least preferred. All right. Then it will be the boat as the second highest in energy, and the second lowest in energy will be the twist conformer. All right. So you guys want to have a decent feel for this. To move between these 2 chairs, you would go chair, half chair, twist, boat, twist, half chair, and then chair again. All right. You guys have these slides. All right. You can look at this. If I had to ask you, which conformer is the highest in energy for a 6-member ring, what would you tell me?
I have
The half chair. All right. If I had to ask you, what is the second lowest in energy for the chair conformation, what would you tell me?
You said second lowest.
Second lowest. Yes, ma'am. What will you tell me? Say that again?
Twist.
The twist. That's right. Twist is the second lowest, right? And your second highest will be the boat. All right. So make sure that you guys have that ordering in mind, and make sure you know how to move between these 2 chairs. All right. This will be my last slide for the day, and we'll talk more about this next class. All right. We want to be familiar with the positions on the chair. There's 2 major positions, and we got to make sure we got this down. We want to be comfortable with the axial position. If you guys look at this really closely, the axis is going vertical from this chair. All right. So any hydrogen that's vertical, either pointing up or down, will be in the axial position, and they're all labeled red here. All right. And anything that goes along the equator, which would be horizontal, would be the equatorial position. And if I look at all these green hydrogens here, these are known as the equatorial hydrogens, or the equatorial position. Okay. It's very important for us when we study these 6-member rings to know, do we have a position axial, or do we have a position equatorial? And we'll talk more about that next class. Being axial in some cases is going to be unstable, and typically being equatorial will be highly stable. So we want to make sure that we can adopt conformations where atoms are in the correct positions. Okay? And that leads us to this conformation that we're going to talk about, which is we can have a ring flip, where a carbon that's axial can flip into the equatorial position. And you'll realize that this equatorial position is better for this methyl group than it is here, because this methyl group is interacting with these 2 hydrogens here, which is sterically bad. But over here, there's not as much interaction with the hydrogen. So this is a preferred conformation. So this ring flip becomes very important. So we have to know which positions we are located to get the proper ring flip conformation. All right, I'll end there because I'm going to keep talking because we need to get into this, but we'll do this on Wednesday. All right, I'm going to go ahead and stop the recording, and I can take any questions anyone has. I'm going to also download the attendance so I can have that in my files. Stop screen sharing. Stop.